this is problem 106 of Neetcode and 50 coin exchange. So in this problem, we're going to be given an array of integer coins, and basically each numbers inside the array is going to represent a certain amount of money that the coin represents. We're going to be given a target amount. Here in the example one that I'm pointing out, the amount target is 12. And we have the coins that represents basically like $1, $5, and $10. And we have to take these coins in unlimited um, number. So we could take like 10,000 billions of times this one, or like 3 times this five. We can use them as much as we want. But the goal is to reach that 12. And it's also to reach that 12 by using the less amount of coin we can possibly take. So to reach 12, the solution will be to take basically uh, 10 plus 2 times the 1. You could also use like 2 times the 5 plus 2 times the 2, which will result in 12, but you will have to use 4 coins, where you can simply use a 10 once and then 2 times a 1, which will return 12 as well. So let's, before that, actually, let's just see at an edge case where there is no answer. For example, if we want to reach the amount 3, but we have only the coin of value 2, well, we can't, so we're going to have to return a -1. Right, so we're also going to have to have a time complexity of big of n times t, and it's going to be the number of coins, and t is going to be the given amount. So we can't really use a brute force approach on it. So we can't really use depth first search. But still, I think that it is great to have an idea of what depth first search can allow us to do. So let's just see what the brute force approach is first. So let's say that we start with the coins 1, 2, 3, and 4, and that we want to reach the amount 6. So let's say that we start at our amount 6, that is our target. We basically have 4 decisions, right? So initially, the first thing we can do is either to take that 6 value and basically subtract 1 to it, or you can subtract 2. You can also subtract 3, and you can subtract 4. So basically, I'm going to take each coin inside the coins we're given, and I'm going to subtract its value to that 6. So now we're going to be left up with, we're going to have a 5. We're going to have 4 here. We're going to have 3. We're going to have 2. Notice that none of these paths actually leads to something that we can basically conclude the problem with. So let's just take a look at the far right branch. We know that at every single run, we're just going to take that particular amount that we are at. So at this particular branch, we are at 2. And we want to basically go for each coins inside the coins we're given. And we're going to subtract its value to the value of coins that we are at here. So now it's 2. So I'm just going to write it down quickly. So we can initially subtract 1 to 2. You can subtract 2 to 2. You can technically subtract you can subtract 3 and 4 to 2, but it will result in something negative. So let's just scratch this branch because we don't really care about them. So 2 minus 1 is going to be 1, and then we're going to have 2 minus 2, which is going to be 0. And now notice that we actually made a path. We don't know yet if it is the shortest path, but we know that we have a path of length 3 that can lead us to 6. So basically we can use 4 in this path. We're initially using 4, and then we're using 2, and it will also be the shortest path, but there will also be other possibilities. For example, here our 1 is basically going to return 0 once we'll have subtracted 1 to it. It will also return a couple other negative values that we just don't care about, because once it's in the negative, it can't come back to the positive. So it will never return an answer uh, that we care about. In this case, we care about receiving a 0. But still, we notice that we have another path here. And this is gonna use 4, and it's also gonna use 2 times the coin 1. So it is not super efficient um, compared to the previous path that used only 2 coins, so the 4 and the 2. And also we're gonna do pretty much the similar, pretty much the same um, concepts on the other branch. So for example, here when we subtract 1 to the left here, so now we're at 5. Well, we're gonna have again or 4 branches, and one of them is gonna be to subtract 4, that's 5. So we're gonna be left up with 1, and on the far left we're gonna have basically 5 minus 1, which is gonna give us 4. And I don't want to do all the combination. I just want to show you that from here, when we have 1, we're going to subtract 1 also in one of the 4 branches, and we're going to have 0. And on this branch where we have a 4, we are going to have a couple of branches, and one of them is going to basically subtract 4 to this. So notice that just from these 3 branches, so let me just highlight them. So this one, and this one, they all give us the path where we take coin 4 and 2 times the coin 1. So this is not super efficient, because imagine that our targeted sum was no longer 6, but it was like 2000, right? Will take quite a while. It will actually lead us to like hundreds of exactly the same solution every single time. So we're gonna have to find a more efficient way. So let's go ahead and actually do that. So the more efficient way is going to be by using dynamic programming. We're going to use a bottom-up solution. So what we're going to do is that we are going to try to see what is the minimum combination for to obtain each each amount. So let's make this clear, okay? We want to target 6, but let's ask the question before. How many coins do we need to reach 0? Well, 0, right? Because we don't need any coins to reach 0. How many coins do we need to reach that value 1? Well, obviously our answer is going to be 1 here, but we might not know it yet. And similarly, we're going to do this for all the numbers up to our amount. All right, so for each of these numbers, we are going to try to see what is the minimum amount of coins we need to actually reach that. So if we start with 1, we're going to see that we have basically just that coin of value 1 that can gives us the amount 1, right? If we have 2, we are going to have basically a coin 2 that will be the wisest solution here. We only have 1 coin needed to reach this amount of 2. But since we don't know it yet, here's the approach that we're going to do. We're just going to take the amount that we want to reach. So the amount we want to reach is 2. And then we're going to go for every single coin inside the coins. And we're just going to retrieve the value of that coin to the amount that we're reaching. So we're going to have 2 minus 1. We're going to have 2 minus 2. we're gonna have 2 minus 3, but that's gonna be negative. So what we do when something is negative, well, we're just gonna scratch it. All right. So this is gonna leave us with basically a value of 0 and a value of 1. So at this point, um, we're gonna have to ensure that the value in a hash map um, for the index 2 or for the amount 2 is going to be the minimum value between what it currently is and also the number of coin it takes to actually reach that amount for each coin. So we can note that at the coin 2 in our for loop, when we reach the coin 2, we can see that it can takes only 1 coin to actually reach the the amount of 2. So we're going to put 1. But before that, inside our for loop, we're going to reach 1 first, right? And we're going to do 2 minus 1, and it's going to give us 1. So now we know that basically the number of coins we will need is going to be 1 plus the smallest amount of coins needed to reach the sum of 1, right? Because now after we retrieve 1 to 2, we are left up with 1, and we know in our hash map we exactly know what is the shortest amount of coin, what is the smallest amount of coin, sorry, we need to reach that particular amount 1. So it's going to be 1 plus basically 1 here. So that's going to give us 2. And in our for loop, we're initially going to go see this coin 1, right? So at first, we're just going to set every single values to something that is really large. So we know we are eventually going to have something smaller than that. So initially, this is going to be set to 2. But then in our second round, when we go see this 2, we're going to do 2 minus 2, and it's going to give us 0. So basically, I will say that the number of coins needed to reach 2, if we take that coin 2, is going to be 1 plus the hash map and the index 0. And the value of the hash map at the index 0 is basically 0, as we can see up above. So this is going to give us 1. And this is where we want to update the value in our hash map at this particular amount to be the minimum between what it currently is, which was 2, and what we just received here, and it's 1. So it's going to be set to 1. Okay? And we're going to keep going this algorithm until we reach our amount of 6. So you can see it this way. For every single amount, we are incrementing basically our amount by 1 every time, and we are getting the smallest number of coin we need to reach this particular amount. So I'm just going to skip forward a little bit here. We can see it at 3, we're also just going to need 1 coin to reach that. At 4, we're also just going to need 1 coin. At 5, we're just going to go through every single values, and we're going to figure out that we need 2 coins at least to reach 5. And when we're at 6, we're going to go for every single coins, and we're going to do 6 minus each coin. So initially, we're going to have 6 minus 1. We're going to have 6 minus 2. We're going to have 6 minus 3. And we're going to have 6 minus 4. So this is going to give us 5. This is going to give us 4. 6 minus 3 is going to give us 3. And 6 minus 4 is going to give us 2. And now this is where the following step will be to make sure this particular this amount, like to reach this amount from 1, we're going to do 1 plus, let's just say our hash map is called h. So we're going to take our hash map at the index of the left up. So the left up is 5. And that is the number of coins we're going to need to reach 6 if basically the last coin that we add is 1. So if the last coin we add is 1, it means that we previously had a grand total of 5. But to reach a grand total of 5, we needed at minimum 2 coins. So to reach 5, we're going to have 2 coins. And then from 5, we're going to need to add 1 coin to reach 6. So this first option is basically going to give us 3 coins at least. And then we are going to go see the 2. So when we subtract 2 to 6, we're going to be given a left of 4. So basically the number of coins that we're going to need is 1 plus the h at the index 4. And the index 4 is 1. So this is going to be 2. Right? Because this is telling us that you basically just need to have 1 coins to reach 4, and then from 4 we know that by using 2 we're going to reach 6. And it is the same principle for the other coins, so I'm not going to go for these last two, but you can see that the hash map at the index 3 is also requiring only 1 coin. Same thing for the hash map at the index 2. So all of these answers will result in 2. So the minimum number of coins we're going to need to reach 6, starting from scratch, is basically 2 coins here. All right. So now we are ready to start coding this. And the first thing that we're going to do is that we're going to create our pseudo hash map. I'm not going to create a hash map. I will just use the basically the amount itself. So right, we're starting from 0 and we're going up to the amount. So each of these values will be from from 0 to the amount. So this is going to be good enough for us to refer a specific value to a value in the hash map using its index. So I will say that this is called DP for dynamic programming. And I initially want to have a very huge amount for each of these amount, because I want to always check what is the minimum value between the current number of coins needed to reach this particular amount and the previous one. So initially I'm going to set something like super big, like infinity, so that we know that whenever we reach the value, even though it's really huge, it will still be smaller than this infinity. But this, we actually want to have 0 up to the amount, so it's going to be times amount plus 1. And at the index 0, we're going to be needing basically no coins to reach an amount 0, so we're setting that to 0. And this is where we want to go for every single amount possible. So I will say for A in the range, and I want to start at 1 because I don't want to go C0. It's not important, as basically we already know it takes no coins to go to 0. So I just want to start at 1, and I want to go up to the last index, which is going to be the amount itself. So I will just say that the bounding index is going to be amount plus 1, so we know we are going to safely reach the amount. And then basically see that this is going to give us like 1. Let's say that in our previous example we had 6. So now this for loop is going to do basically it's going to do 1, 2, 3, 4, 5, and 6. So we know that for each of these, we're going to go see the coins. We're going to go see all the coins we have. And we want to subtract these coins to the current value of A. So I will say for C in coins. And I want to check if that particular if the result of the value A minus the coin is at least 0, hopefully greater. So if A minus C, if this is greater or equal to 0, right? I want to set the hash map at the index A to be the minimum value between its current values, so dp index A, and also 1 plus dp A minus C. All right, so notice that at 1, right? Let's say that we have, so like our coins are equal to 1, 2, 3, and 4, just like in our example, and that the amount is 6. So now we're going to go for 1. So A is initially going to be 1. Now we're going to go see every single coin. So we're going to go see 1, and we're going to do basically 1 times the coin 1. So it's going to be 0. And we're just going to check if that particular value at this index 1, which is initially going to be set to infinity. So we want to make sure that this is going to be the minimum value between that its current value, which is infinity, as I just mentioned. And also 1 plus A minus C. Notice that A and C are both 1, so it's going to be 1 plus the hash map at the index 0, which we initiate to 0, so it's going to be 1. So we know that at this exact first round, the hash map at the index 1 is going to be set to 1. Then we're going to go C2, and we're going to go for all the coins inside the coins, and we will subtract this to 2. So we're going to have this A, which is going to be equal to 2, and it's going to be basically 2 minus 1 initially, and then we're going to have 2 minus 2, the other coin, and the next coin is going to be 3, but 2 minus 3 is not going to be greater or equal to 0. So all the cases after this will fail this if statement. So basically we're just going to have 1 and 2, the coins that will work, and basically the hash map at the index 2 is going to be the minimum between infinity, right, the initial value, and 1 plus the DP at the index A minus C. So for the coin 1, we're going to have basically 1 plus the index of 2 minus 1. So the index 1, which we previously set to 1, right? So it's going to be set to 2 because it takes 2 times the coin 1 to reach a value of 2. And also on the second coin, we're going to have basically 1 plus dp of A, which is 2, minus coin, which is 2. So 2 minus 2, 0. So it's going to be set to 1. So we know that with only 1 coins, we can reach we can reach that amount. So after this, what is left for us to do is basically to return the amount. So the hash map at the index of the amount. And you want to check if this is not equal to infinity, because if it is equal to infinity, it means that something went wrong, in which case the problem explicitly mentions to return a minus 1. So if this is not equal to infinity, all right, otherwise we are going to be willing to return minus 1. And I forgot F there. All right, so that's the entire solution. So notice that also in terms of time complexity, we're quite efficient. So we're going basically through every single amount possible up to the maximal amount. So we're going to go for 1, 2, 3, 4, 5, 6, 4, 5, 6 if the amount is 6. And we're also going through every single coins each time. So we're going to have basically time complexity of big O of n times t, where n is the number of coins and t is the given amount. And if in terms of space complexity, well, we are going to store basically the length of the amount inside our pseudo hash map. So this is going to give us a space complexity of big O of t. Let me just indent this. And now we can test this out. So let's see the results. And it works. Awesome. So I hope you learned from this video, and I hope to see you in the next one.